If you can get here Monday before school, I can do that. Yeah. If it's after that, then no. Okay, so 5.5, I know y'all started it, but y'all are going to still, bless you, act surprised and full of bewilderment and wonderment, right? Yeah. Like, ooh, wow, okay. So everything you did in 5.4 with sinusoids, all we're going to be doing now is applying those to real-life situations. And when you can apply sinusoids to real-life situations, we usually call that type of motion that the object is experiencing, we call it simple harmonic motion, which means it's sinusoidal. It's increasing, then it's decreasing, then it's increasing and decreasing at regular intervals, right? There's no obstructions to it. So one of the best examples, one of the classic examples, is the old Ferris wheel, right? So we do have a Ferris wheel at the Canal County Fair. It's not one of the most exciting rides at the fair, right? Like the Zipper or, as I mentioned earlier, the Sizzler. But when you think about how the bolts on the Ferris wheel might not be cranked down all the way, it does add an extra element of excitement to the Ferris wheel, right? Is it coming undone? Am I going to fall? Okay? So the Canal County Fair Ferris wheel is a 3-minute ride that takes its riders on a thrilling, right? Bolts might not be tight, up to a maximum height of 105, where you might be able to see your house, and down to a low point of 5 feet above ground. Assuming that the Ferris wheel rotates at 6 revolutions per minute. 6 revolutions per minute is a measure of what? Omega, which is, that's right, angular velocity. Y'all remember that lesson? You're allowed to use anything you've learned in the past as we move forward. That is angular velocity. And conveniently, this guy is not on the ride just for thrills. He's there on business, on purpose. He's a math student. So he starts his stopwatch immediately as the ride starts at its low point. So we could assume he's the last one on the ride. When the ride gets going and he's at the low point, he starts his stopwatch. So t equals 0 corresponds with the low point, which of course we know is 5 feet. Here's part A. Sketch the graph of the rider's height above ground, h, in feet, as a function of the time he's on the Ferris wheel in seconds since he started his stopwatch. Okay, so let's go ahead and set up the graph. If we could set up the graph, everything else is going to just be so much easier from that point on. Now this graph, since he started at t equals 0, is going to take place in the first quadrant. So we're measuring his height, I'll call that h of t, in feet, graphed against time t in seconds. So this is why we need to be using radians for all of these applications. If you're ever going to assign units to your x and y axis, it has to be because there previously were no units. So if I use radians on my x-axis, which are unitless, I could assign seconds to it. And of course, we're going to be looking at sine and cosine ratios on the y-axis, and the ratios themselves are always unitless. So now we can assign units to it of feet. All right, the easier of the two axes, vertical or horizontal to set up, is the vertical axis. We know that it hits a low point of 5 feet and a high point of 105. So if you come to your graph, just call that 5. It's a little distance above the t-axis. And then I'm going to come up here and just call that 105, this high point. So that's going to end up being the range of this sinusoid. Remember, they stay bounded. It's going to stay between 5 and 105. The next thing you could quickly and easily do is draw a line exactly halfway between your high and low. And with any luck, it'll show up here. Come on, Wi-Fi. There you go. And now to label it, how do you find the midpoint of any two numbers? You average them, right. So 105 plus 5 is 110. What's half of 110? 55. Good. So 55 is the midpoint. And that's significant because that's going to be your sinusoidal axis. So now we're going to just draw a dotted line straight across. It's not a horizontal asymptote. It's just your sinusoidal axis. All right, so that's the midpoint. You're going to go up to 105, down to 55, down to 5, up to 55, up to 105. Okay, so there's the vertical axis. Now the horizontal axis is always the more fun of the two. But being a good math student, right here at t equals 0, it said he started his stopwatch at a low point. So we know there's going to be the 0.05, which is a critical value. Good boy or good girl, good math student. Now, we need to figure out the period, the length of one cycle. We were told that the angular velocity was 6 revolutions per 1 minute. We need to figure out the length of one cycle, the period, right? That's the length, which in this case we're measuring length in seconds. So it's the time length of one cycle. Or cycle is also known as one revolution. So the angular velocity gives you revolutions per minute. We want minutes per revolution. So how is the angular velocity related to the period? Any idea? They're actually reciprocals of each other. The angular velocity is also known as the frequency, f. They're interchangeable. Angular velocity is the same as frequency. So the period is going to be 1 over the angular velocity, 1 over the frequency. Frequency and period are inversely related. So that's going to be 1 minute per 6 revolutions. Now what we want to do is make the denominator 1, okay, instead of a 6. So you could say it's a 1/6 of a minute per 1 revolution. But we also want our period to be measured in what units? Not minutes, but what? Seconds. So let's go ahead and convert it. 1 minute is the same as 60 seconds. So it takes 60 seconds to make 6 revolutions. And if we simplify that, that's 10 seconds per 1 revolution. And that's what we want. Because if you write it outside the fraction, that's 10 seconds for 1 revolution. And that means that 10 is our period. It takes 10 seconds for it to go around 1 time. Now, if your denominator doesn't always come out conveniently to a 1, let's go back to here. If it was 1 minute per 6 revolutions, you could just say that that's 1/6 of a minute per 1 revolution, and then your period could be 1/6. Okay? But in this case, it works out nicely. Now, you probably could have figured that out just by common sense, right? If it makes 6 revolutions every minute, that's going to be 1 every 10 seconds. Okay? But this is the mathematical way to do it. So now we know the period. So we can come back over here to our graph, and I'm going to come out not all the way to the end. I'll come out about halfway. And because 0 is where we started, and that's the critical value, I can go ahead and just put 10 there. And now, like we did with our sacrificial axis, which we don't need here, we'll bisect it. That gives us 5. And we'll bisect it again to get 2.5. And now remember, there is no more important value of time on this ride than 2.5 seconds. Because every 2.5 seconds, now the rider is going from a low to a mid to a high to a mid to a low to a mid to a high to a mid. So now we can just go ahead, and remember 0 is a critical value. We can add another critical value between 5 and 10 halfway, and add 2.5, and we get 7.5. So they're the 5 critical values that we need for 1 cycle. But since I have more space, I'm going to go ahead now and just kind of eyeball it like we've been doing, and just try and keep them about the same distance apart. And now just start labeling it, adding 2.5 seconds. So I'll get 12.5 here. I get 15. I get 17.5. And the next one is going to be 20. Okay? Now, if you have a low point or a high point, you know where all the rest of the critical values fall. If you have an axis point, you need 2 points because you need to know if it's an axis going up or an axis going down. We conveniently started at a low point, so now it's going to be super easy to just fill in your critical values from left to right. So here we go. We'll do that. 2.5 is an axis, 5 is high, axis, 10 is back low, axis, high, axis, low. So you don't have to draw necessarily 2 cycles, 3 cycles. For sure you have to draw 1 cycle. Now remember, I said I always want at least 1 point to the left of the y-axis. In this case, we don't really need that because he started his watch at 0, going back to the left would be negative time before the ride started. Now, sometimes negative values are meaningful. If he started his stopwatch late, we can kind of extrapolate backwards to see where he was when it started. But this was a good math student, right? At t equals 0 when the ride started, so we don't need negative values. All right, so now just to finish off the graph, you just connect them with your pretty quarter cycle arcs. La, 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 la. And then we'll turn the corner. And of course, the ride is continuing on, but we don't need to graph all of them. And now you have your pretty graph. Beautiful, beautiful, beautiful. Once you have the graph, part B then says, assuming that H is sinusoidal with respect to time, write a particular equation and then confirm it on your calculator. All right, so we're going to write an equation. It's going to be called H instead of Y or F, and we're using T instead of X. Let's go ahead, though, off to the side here and gather our information like we've been doing. So there's the absolute value of A, absolute value of B, C, D, and then, of course, we need the period and the range. All right, so if we can find these, then it's going to be real easy just to drop them into our equation when we ultimately write it. All right, so what is the amplitude now? You can get this information pretty easily from the graph. 50, yeah. The amplitude is half the distance between the high and low. Well, if we're at 55, it's 50 to 105 and 50 down to 5, so it's 50. What significance does 50 feet have in the context of the Ferris wheel problem? It's the what of the Ferris wheel? Good. It's the radius of the Ferris wheel. This Ferris wheel has a radius of 50 feet or 100-foot diameter. Excellent. Now, B, remember, is not something you can necessarily get straight from the graph. It's the number of cycles in 2 pi, which is like 6.28. I can't just look at that and tell what fraction of a cycle I have. So B, typically, we don't get from the graph. We get B from the equation. We convert it to period, then sketch the graph. If we start with the graph, we actually start with the period first, and then we convert it to a B value. What did we say the period was? 10. Good. 10 seconds for 1 revolution, so 10 seconds. And that was the reciprocal of the angular velocity. So I'm going to put the period as 10. Now remember this formula. P was equal to 2 pi over the absolute value of B. If you just take that same equation and you solve it for the absolute value of B, you get 2 pi over P. Right? Kind of the same thing, you're just dividing by the period now. So if the period is 10, what's 2 pi over 10? Pi fifths. Good. So B is pi fifths. So between 0 and 2 pi, which is like 6-ish, we only see pi fifths of a rotation. A little bit more than a half of a rotation. All right, now C, remember, we hold off on C because our phase shift depends on whether we're calling it sine, cosine with a plus or minus A. That's the last thing that we do. The D value, though, we can get from the graph. What is it? 55. That's your sinusoidal axis. That's the midpoint of the high and low. We already found it. It's 55. Positive 55. All right, now the range is real easy. We could get that actually without the graph because it told us. It's going to be from 5 to 105. So for what it's worth, we'll just go ahead and include it here. Bracket 5 to 105, close bracket. If you want to put feet on the outside, there are units there. Same thing on the period. If you want to put seconds after it, there are units. But this is just us gathering information. Okay, so now we're ready to write the equation. So here's part B. Part B. Stop. There we go. We got H of T equals. Now I'm going to leave a little bit of space here. I'm going to put A. I put the space in front in case we wanted to include a negative value of A. Remember this. This is kind of important from the previous section. If we start at a low point, that's going to be a negative cosine. If we start on a high point, that's going to be a positive cosine, right? Cosine always starts on the extremes. If we start on an axis going up, that's going to be a sine, positive sine. And if we start on an axis going low, it's going to be a negative sign. So we have the option of writing any one that we want. What would be the easiest one here? Negative cosine. Yeah, everything except the negative cosine will require a phase shift. which you're welcome to do. But because he was a good student and he started his stopwatch at a low point, if we use negative cosine, we will not need a phase shift. So that's what I'm going to do for the main one. So negative 50 cosine, parentheses, the b value comes next, which is pi fifths. And then, of course, because we don't need a phase shift, we could just put a t instead of parentheses t minus 0, and then, of course, plus 55. So I'm going to box that one because that's the main one. That's the one I'm going to use. But if you don't want to do that, let's go ahead and just write one more. Or you could have h of t equals, let's do a positive sign just for contrast. We could do positive 50 sine pi fifths, and now another set of parentheses, t plus or minus something plus 55. And what would the phase shift be if we wanted a positive sign? Minus 2.5. Good. 2.5 is the first positive time where he's on the axis going up. You could go a full cycle away to 12.5 if you want. But in general, try and keep them kind of small. So t minus 2.5. That's another perfectly acceptable answer to part B. So on your test on Friday, you'll be doing something very, very similar to this. You're going to graph it first, then you're going to write an equation. The graph is going to be correct for everybody. Everyone's going to have the same graph. But there's infinitely many correct equations for part B. And as long as you have one of them, you're good. Now, before you start using your equation to answer questions, you better check to make sure you have the right equation. If you graph your equation now in Y1 and you graph it in the window that you graph this in, it should be pretty much the same, right? So we could verify. Now, what mode do we need to be in? Radian mode. Okay, so let me go to my calculator. Close your eyes and pretend you don't see anything here so I can kind of clear everything out. So you don't see anything. Clear. Okay, good. So let's go ahead and check the mode first. I am in radians. That's good. Radian mode. If you're in degree mode and you take the test in degree mode, that's going to be downright unfortunate. I'm not going to be very sympathetic if you take the test in degree mode. It's going to be wrong, 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 and then next time I guess you'll be in the right mode. So check the mode first. We're in radian mode. Now I'm going to go to Y1. It's wide open, and I'll type in the easier of the two. The first one we did, negative 50 cosine of pi fifths. So notice it opened the parentheses. Alpha y equals, remember, is your horizontal division bar. So if you want to go with that, maybe it looks a little prettier. And of course, we're in function mode. So we're always just going to use our independent variable in the calculator to be x, regardless of what we call it on our paper/iPad. Close the parentheses. There's no phase shift. Plus 55. Now, if you just hit zoom 6, you're going to get a very meaningless graph, okay? So what you're going to do instead is go to your window and type in the window that we just did right here to see if it matches. All right, so I'll go ahead and get rid of this screen. You have yours in front of you. Our X-min, I'm going to go ahead and put -1 instead of 0. That way we can see the y-axis. We went out to 20 seconds, so that sounds good to me. I'll go out to 20. Your X scale, you can either turn it to 0 because you don't really need tick marks, or in this case, if you want to put it at 2.5, since 0 is a critical value, you'll actually see the critical values every 2.5. That's fine. Your Y-min, since this takes place in quadrant 1, we'll put -1 so we could see the x-axis. By the way, what's the significance of the x-axis in the context of this problem? If h of t is measuring the height above ground, yeah, the x-axis is ground level. It represents the actual ground. So we'll put -1 so we can see the ground. And our y-max was 105. I would recommend going something above it because your calculator always uses the top and bottom of the screen for writing. And then your y-scale, you can just turn that to 0. You don't need to see anything on your y-axis. You'll get fat axis if you leave it as 1. And who wants a fat axis? All right, so now we hit graph, and you should see it matching your graph, and if you pay attention as it graphs, you can see it go up and down, and you can imagine that you're riding the Ferris wheel virtually from the safety of your math desk. Ready? Wee! Well, woo! Yeah! See? Fun. Now, but for the color, does that look like ours? Ours is, of course, more awesome, but it kind of looks like ours. Here's one thing I would recommend you do before still you answer questions. Verify a point. If you look on your graph at 7.5, this is just an arbitrary selection. At 7.5, we're on the axis, which is 55, coming down, right? Let's verify that. Go to your graph, hit trace, and just type in 7.5. It's waiting to accept something. You should be at 55 coming down. Are we at 55 coming down? Yep. So there's a numeric indication now of your awesomeness. So now moving forward, you know that this graph and that equation are correct. If you don't verify, or you do and you get the wrong thing, then you're just kind of accumulating X's after that. So don't do that. Okay, so now we're ready to proceed with confidence and correctness. Part C. How high above ground is the rider at 48.5 seconds? At this time, is he coming up or down? So just like with the logistic equation, I'm going to ask you two things. I'm either going to give you an independent variable and you find the dependent variable, or I'll give you the dependent variable and you find the independent variable. Is 48.5 an independent or a dependent variable? Is it a T or an H value? It's a T, so it's the independent variable. So remember, on your paper, you have to show me what it is you're putting into your calculator. So all you have to do is put H of, and then write the time, 48.5. 48.5. Now there's two ways to do it. If you go to your calculator screen and you hit trace again, and you type in 48.5, in this case, it's going to give you an error. Does that mean that at 48.5 seconds, the Ferris wheel bolts came undone and it broke? No. If you're going to be typing something into your graphing screen, it has to be in the window that you typed it in. And we only went out to 20. So you could set that to something greater than 48.5 and then just patiently wait for it to graph again and imagine you're on it. But who has that kind of time? I don't. So here's how I'm going to recommend you do it, but I'll show you the other way at the end. From the home screen, if you just hit alpha trace, which is your shortcut to all of your equations in the y's, we put ours in y1. So just hit enter or type in 1, open parentheses, and type in 48.5, close parentheses. It's like evaluating the function at 48.5. You hit enter, and you write down 3 decimals, 25.610. And again, remember, I'm a big fan of truncating. So you can put 611 if you want as well, and that's feet. I'm going to put above ground because, believe it or not, sometimes in some problems we might go below ground. But in this case, all positive numbers are above ground. So at 48.5 seconds, we're 25.610 feet above ground. Heading up or down? Well, we can't really tell from that number, right? So what could we do? You could graph it, but then we should have done that to begin with. I'm not going to do it that way. Would it be helpful to know where we are in the near future after this moment? Yeah. So all you need to do is plug in a number after 48.5. Now, don't plug in like 50. That's way too far away. Don't even plug in 49, because what could happen is if you plug in a number too far away, you could have already turned the corner, and you could be coming back the opposite direction. So what I would recommend is if you just look at like 100th of a second later, in this case, that's pretty safe for a 10-second interval. Just, you could recall it, second enter, or do alpha trace 1 again. Just look at maybe 48.51. So that's 100th of a second later. That's pretty safe. In 100th of a second, you're very unlikely to have turned the corner. But you can go even smaller than that if you want, 0.501. And then you just compare the two numbers. So 100th of a second later, we were what? Higher or lower? Lower. So the odds are is we were coming what? Up or down? Down. So that's all you need to do. So if we're coming down, just put HE of 48.5 equals 25.610 feet above ground, and then we'll just put coming or heading, whatever you want to put, down. So that's one way to do it. The other way to do it, and some of y'all might prefer this, is just to go to your window and set your X max to something greater than 48.5, like 50, and then patiently wait for it to graph again. Yeah. And now you could just hit trace, And don't scroll over there because it's not going to hit 48.5. When you hit trace, you can actually just type right over it, 48.5, and now there you are. Your numbers are at the bottom, 25.610, and now you can see it's blinking at a point where the graph is doing what? Coming down. So that's another way to do it. That's less fun, or maybe you think it's more fun. It's just another way to do it. Okay? All right. Yes? Yes, you may. All right. Any questions on whatever this is, part C? I give you an independent variable, but there's a twist, right? Are we going up or are we coming down? And then make sure you always put units on your final answer. Okay, A, B, C, I guess D comes next. So here's part D. At what positive time is the rider 88 feet above ground? That's a dependent variable now, but notice not just any old 88 feet, heading down for the third time. Holy moly smokers. We want to know where he's 88 feet coming down for the third time. So on your paper, since now I'm giving you the dependent variable, you have to show me h of t equals 88. And then below there, you're going to put t equals, and then we'll find it on the calculator. Now, I'm not going to make you set 88 equal to the equation and solve algebraically by taking the inverse sign. We haven't learned inverse sign yet. So you're going to be able to do this on the calculator. So you go to y equals, find the next available y, type in 88, and hit graph. Now, if your window is not big enough on the x, you can expand it. We need to know where he's at 88 for the third time coming down. The first point of intersection is 88 feet, but that's where he's going what? Up. So he's going up, and now he's coming down. So the second point of intersection is 88 coming down for the first time. So we want to go 2 cycles over. There he's at 88 coming down for the second time, and there he's at 88 coming down for the third time. So we actually want the 1, 2, 3, 4, 5, 6. We want the 6th point of intersection on this graph. And if you didn't see that, again, extend your X max so that you do see it. So now we go second trace number what? 5. Good. And now for the first curve, you can hit enter. For the second curve, you can hit enter. The guess is the important one. This is where you want to scroll over precisely to the one you want, because if you're not close enough to it, it'll find the wrong one. There you go. So it looks like I'm there. I'll hit enter, and I get a blinking confirmation. Okay, so enter, enter, first curve, second curve. Guess you need to scroll over. There's your blinking confirmation. So I'm going to put 26.352. Again, I'm a big fan of truncating, and that's my final answer. So I'll put seconds behind it. There he is. So now you can answer any question of that type. 55 feet going up, 20 feet going up for the 5th time, whatever. You just find the right one, find the point of intersection, scroll over to it. All right, any questions on those two? Giving you an independent or a dependent variable. Pretty easy stuff, right? Stuff you've done before. All right, A, B, C, D, E comes next. Now, E is where it starts getting kind of fun. Not that you haven't been having fun. During the 3 minty ride. Now, I don't know what 3 minty ride means. I don't know if he's eating a York peppermint patty while he's riding. But whatever. During the 3-minute minty ride, for how many seconds was the rider above 100 feet? Wow. Show the work that leads to your answer. Okay. For how many seconds over the entire trip was he above 100 feet? So here's the first thing we need to do. Let's go to our paper. Since 100 feet is a height, I'm first going to show h of t equals 100. That's the first thing I'm going to do. Then I'm going to go to my calculator. I'm going to go to Y2, get rid of that 88, and type in 100. And then hit graph. Whee! Now notice, he is above 100 anytime the graph is above the red line, yes? So if you look at from t equals 0, he hits 100 going up, and then he stays above 100, and then he hits 100 coming down. If I can find those 2 values right there on his first rotation, where it intersects 100, I could find the distance between those 2 time values to figure out the duration that he's above 100 each rotation, right? Does that make sense? And then all I have to do, since they're all symmetrical, is figure out in 3 minutes how many cycles there were and multiply that duration by that time. So there's my plan of attack. Let's go ahead and find the points of intersection between these two consecutive t-values. It doesn't have to be the first two. It could be the second set of two, the third set of two, whatever. The numbers are just smaller for the first set, so those are the ones I'll find. Second trace, number 5, enter for your guess, and now scroll over, and I'm just going to scroll over to the first one. Looks good, and I'll hit enter. Now on my paper, I'm going to put t equals, and I'm going to write it down to 3 decimals, 4.282 seconds. Okay? 4.282 seconds. Now, I'm going to have to reuse that number, am I not? I'm going to have to find the other one and then subtract them to find the duration. When do we want to use a rounded or a truncated number for a subsequent calculation? No. Never. So because I'm going to have to reuse that, I'm going to store it. And you need to get in the habit of storing values. So if you go to your home screen, second mode, flush, just to get rid of it, clear. If you hit the X button and hit enter, boom, it has it temporarily stored as the X variable. It's going to override it, though, when you find the next one. So what I'm going to do now is just hit stow right above the on button, and I'm going to hit alpha A. A is right below the green alpha button. And hit enter. And now it's locked in as A. Now, if you store it as A on your calculator, here's what you're going to want to do on your paper. Put equals A on the back end of it. And now you can refer to it as A in your calculations. And it's a reminder to use the calculator stored button. All right, we got one more to find, and we're going to do it very similarly here. So now, second trace, number 5. Enter. For your guess, scroll a little bit to the right, hit enter, and there's the second one. So on the paper, t equals 5.717 seconds. You still want to report it to 3 decimals, but now I'm going to put equals B. I'm going to store that as alpha B. So I'm going to call it B on my paper. So again, to store it as B, we'll just go to the home screen, second mode. Now, you don't need to hit X enter. You could just say X stow alpha B, which is just to the right of alpha A. And if you hit enter, it'll show up, 5.717. Good thing we stored the first one as A because it overrode it immediately when we found the next one. All right, so now that we have them stored as A and B, we are ready to answer the question. Okay, so I'll do that right here next door. So the time spent above 100 feet is, and here's the work that leads to our answer. I need to figure out the duration, so B minus A. That gives us the duration spent above 100 for one cycle. But I need to multiply that by however many times he rotated. So to do that, I guess the easiest way is just to set your window out to X max for the entire 3-minute ride, which isn't how many seconds for 3 minutes? 180. So let's just go ahead and set that to 180, and then we'll hit graph, and we'll see the whole ride right here very fast, right? Wee, yahoo! Yeah! And there's 100. Okay? And now all you have to do is count the number of peaks. It doesn't look very symmetrical, does it? But we know, in fact, that each of these actually is symmetrical to each other. It just is trying to squeeze them in. So let's count the peaks that we see in the window above the red line. Very carefully, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18 full times that he rotated above 100 and came back down. So 18 full cycles. So now all we got to do is come over here and multiply that by 18. So 18 times B minus A is all you need to show for the work that leads to your answer. And when I see B minus A, I'm going to look over here to the left. I'm going to be like, oh, there's A and there's B. And now all you got to do is go to your calculator and type it in pretty much exactly as you see it right there. Back to the home screen. 18 parentheses alpha B minus alpha A. close parentheses, hit enter. And that's now your final answer, 25.841 or 842 seconds. Those are the only two answers I would accept, 841 or 842. So if you didn't use the stored numbers and you were off in the third decimal, it would be RONG. Wrong, okay? Now, this is a good statistic that you could give to the carnival operator, right? He could use this in his advertising, right? Come ride the Canal County Ferris wheel and get high for almost 26 seconds on my ride. Yeah, and you'd be like, oh, yeah, high for 26 seconds. And you ask him, what do you mean by high? And he goes, well, above 100 feet. And you're like, good. That's the good, clean kind of high I was hoping you were advertising about, right? Of course. And then you ask him, are those bolts tight? And he goes, what bolts? And you're like, good. Yeah. Okay. Now, we're not done with the problem. Part F, what is the linear velocity of the rider in miles per hour as the Ferris wheel rotates? So I am no artist by any stretch of the imagination, but you are on the Ferris wheel right here. There's your head. Your arms are in the air because you're having a good time, and you're sitting down in a chair, right? And now notice your hair is blowing in the breeze because you're rotating through space, right, on a 55 radius Ferris wheel up to heights of 105 feet above ground with loose bolts. And you want to figure out what the linear velocity is, okay, in miles per hour. So what is the formula for linear velocity as it relates to rotation? I know you still memorized the formula. V for linear velocity equals, I heard it, R times, not W, omega, not W, omega, okay? Do we know the radius of the Ferris wheel? Yeah, do we know the omega of the Ferris wheel? Sure. Now, if I didn't give you the omega, if you had the period, you could find omega. Because how are omega and the period related? They're reciprocals of each other. Yeah. Not inverses, reciprocals. All right, so we want it in miles per hour, so let's go ahead and plug in. What was the radius of the Ferris wheel? Yeah, not 55. I said 55 earlier. Sorry, bad memory. It's 50. It's the A value, right? So we'll plug that in right here. And I'm going to put units because, remember, we want miles per hour at the end. And omega, we got quite a few omegas. It's probably best just to use the one I gave you because you know it's correct. And it's probably a little bit closer to miles per hour. So instead of 1 per 10, I'll just use 6 revolutions per 1 minute. And I'll write it like that, 6 revolutions over 1 minute instead of RPMs. Now, if you just multiplied together, are we going to get miles per hour? No, we're going to get feet revolutions per minute. Not good. Yeah, that's a pretty good unit. So we need to convert feet to, that's right, miles. We need to convert minutes to hours, and we need to convert revolutions to radians. Excellent, excellent. So this is just stoichiometry. So if you want to put 50 over 1, here we go. We want feet to divide out. We want miles to appear. Y'all are culturally literate. 1 mile is how many feet? 5280. Good. So you still remember that. And now it's fun to go. Feet divide out. All right. Let's do time next. We got minutes in the bottom, so I want minutes to divide out. I'll put it in the top. I want hours to appear. 1 hour, of course, is 60 minutes. I didn't ask y'all. I'll just take the liberty of doing that. If you don't know that, you should memorize it. And now we got revolutions to divide out. So 1 revolution in the bottom is how many radians in the top? 2 pi. Now, if you want to put radians, RAD, it's fun to write the word rad, but you don't really need to. Now your revolutions divide out. And if you look at the units that are left, you get miles per hour. And so now you know that you're going to get the correct answer. So now you just go to your calculator and you type it in exactly as you see it. And of course, you don't need to worry about the ones because that's the identity element of multiplication. So flush to get a clean bowl there. And now you got 50 times 6 divided by 5280 times 60. And in this case, we are multiplying by 2 pi. so you don't have to worry about parentheses. But remember, if you're ever dividing by 2 pi, you need to put 2 pi in parentheses or divide by 2 and divide by pi. So that should be right. And you get 21.419 or 420 mph. So there you go. You are traveling through space at 21.5 almost miles per hour. If this Ferris wheel was set up inland a park, you would get pulled over for speeding in the middle of the ride, right? Because you are exceeding the posted limit of 20 miles per hour. Yeah, that is how fast you're going, all right? All right, so this makes a fantastic problem on a test, right? Okay, now this was a good math student. He was diligent enough to start his stopwatch at t equals 0. But then you got some idiots that you send to the fair to collect data for you, and they think they're there to have fun instead of collect data, and they're like, oops, I forgetted to start my stopwatch. Okay? Like the guy from example 2. If the writer from example 1 started his stopwatch when he was 12 feet in the air going up, idiot! What would the new equation of his height be above ground? Okay, so now t equals 0 has to correspond with 12 feet above ground going up. Okay, now 12 feet above ground is not a good value. If he forgot to start it right away, he should have waited till he was halfway up or at the top or halfway down or back at the bottom. But he is an idiot, pre-cal student, and I don't know why I sent him. But he's just riding the ride going, can you fix it? And we're like, yes, we can fix it, you idiot. Just enjoy the ride. All right. So here's all you have to do to fix it. We want to know then, we want 12 feet going up to be the new y-intercept. So if you just set h of t equal to 12, you can reuse your information from number 1. All you got to do is graph 12 instead of 100. Whoa, we don't need to see all of them. Stop. Let's just go back out to 18 seconds instead of 180. All right. Find where it intersects, where he's at that intersection going up. The first one's right here. You could also go way out here. We want that first positive intersection now to correspond with 0. So if I can find the t value where it intersects, all I'd have to do is pick my graph up and move it which direction for that to be the new y-intercept. Left. Okay. So let's go ahead and find the point of intersection. Second trace, number 5. Enter, enter. And now for the guess, I'll scroll over here. There's where he's going up. If I said going down, you would find the second point of intersection. It's 0.852. So I'll put t equals 0.852. All right, so now all we have to do, come back up here, grab the original equation you had, and now we're just, because we started late, we are going to add that to our C value, whatever it was originally. Now for us in this case, luckily, the C value was originally 0. So to shift it left, or because we started late, it's going to be t plus 0.852 plus 55. Now if you had used the other one, let's say that you had used the positive sign and you already had a C value, no problem. You just take the old C value, it was t, when we used positive sign, it was t minus 2.5. Just go t minus 2.5 and again add 0.852 to your old C value, and then you can get a new one. Now because we use 0.852, which is a rounded number, I'm not going to make you report infinitely many decimals. If you go back to your equation then, let's get rid of the 12, and you just type in that new equation when you added that intersection point to it. So that would be x plus 0.852, close, close, and then plus the 55. You can confirm. Some people want to shift it the wrong way. Because we wanted to shift it left, it had to be plus. Notice, what is your new y-intercept? Well, if you hit trace and you hit 0, notice it's exactly 12 going up, right? Is it exactly 12? No. Why not? Right. We use only a 3 decimal answer, which is fine. If it's close to 12 here, I'm not going to count off. We're not going to report more than 3 decimals. But you could see there that it's blinking at 12 going up, so you know it's the right answer, okay? So if you want to shift left, you have to add. Remember, he started late, so we're adding time to the original. All right, so that takes care of example 1 and 2. Those together, 1 and 2, make a fabulous free response question, okay? So now you can get started in your worksheet. If you haven't already, have a fantastic rest of the day. And I'll be here tomorrow.